It is my great pleasure to welcome you to the world of learning new concepts and current trends, so let's start. Imagine needing to update a tutor's email address in a registry containing thousands of student entries. We are looking at a spreadsheet where the same tutor's contact information is repeated across various records. Because this structure tracks student and staff data in the same row, that email is tied to every individual that tutor teaches. To change it, you have to find and edit every instance manually. If you miss a single row, the data becomes inconsistent. This is an update anomaly. It occurs when a system requires multiple changes to record one single fact. To prevent this, we move toward a normalized structure. This process relies on functional dependencies, the logic that a primary identifier, like a student ID, should dictate exactly what data belongs in a row. The goal is for every piece of data to depend exclusively on its primary key. We achieve this by passing the table through three specific filters. The first filter is first normal form, or 1NF. This requires every cell to contain an atomic value, meaning no lists or repeating groups are allowed within a single entry. In our starting table, one student record has two modules stored in a single cell, preventing efficient database searches. We resolve this by separating the entry into distinct rows. Now, each module occupies its own cell, meeting the requirement for atomic data. We now have a consistent grid, but by duplicating the student information to accommodate multiple modules, we have introduced significant redundancy. This leads us to the next filter. Second normal form, or 2NF, identifies and removes partial dependencies. Student ID alone cannot identify a unique record. We need a composite key, student ID and module ID. But module cost depends entirely on module ID. We extract these into a separate modules table, leaving a copy of module ID in the student table as our foreign key bridge. 2NF ensures that every attribute relates to the entire primary key, eliminating data that only partially belongs in the table. Third normal form, or 3NF, states that no non-key attribute can be determined by another non-key attribute. Examine the 2NF student table. The tutor's email is determined by the tutor's name, not the student's ID. This transitive dependency relies on a middleman. We move the tutor details to a dedicated table, using tutor name as the foreign key link back to our students. 3NF results in a structure where every attribute is an independent fact about the primary key. Compare the messy spreadsheet with the final 3NF triad. Data is distributed logically. When updating a tutor's email, we edit it once in the tutors table. Through foreign key links, this change accurately reflects across the entire database. This three-step checklist provides a standard for data validation: 1NF for atomic values, 2NF for complete dependencies, and 3NF for direct dependencies. Normalization provides the structural foundation required for data to remain consistent and accurate as systems scale.
Today we're diving into relational database normalization, the process of organizing data to reduce redundancy and improve integrity. First normal form, or 1NF, requires every cell to contain an atomic value. No lists or repeating groups allowed. Second normal form, 2NF, moves us further by ensuring that every non-key attribute depends on the entire primary key. Third normal form, 3NF, goes even deeper, removing transitive dependencies where non-key attributes depend on other non-key attributes. The goal is a lean, efficient database where every piece of data is stored in exactly one place. Normalization prevents update anomalies and ensures your data remains consistent as your system scales. From atomic values in 1NF to removing middlemen in 3NF, these steps are the foundation of good database design. Start normalizing your databases today for a more robust system. Thanks for watching.